Welcome to lecture 9. In this lecture we talk about rank of a matrix and linear independence of its rows and columns. The number of pivots in the row reduced echelon form of a given matrix A is called the rank of A. We have shown in the last lecture that whatever the algorithm we apply, once we reach the row reduced echelon form, this is a unique matrix. So start with a matrix A and apply any type of algorithm to get to row reduced echelon form, that will be a unique matrix, and hence the definition of rank is well defined. Now suppose B is a matrix in row reduced echelon form. This matrix B is invertible, implies that it does not have a zero row. B cannot have a zero row. In fact, it is if and only if. But then this implies that B is equal to identity. Therefore, a matrix in a row reduced echelon form is invertible if and only if it is equal to the identity matrix. So using whatever we proved in the last lecture, we can make this conclusion that a square matrix is invertible if and only if its row reduced echelon form is equal to the identity matrix. A square matrix, you start with a square matrix. This can be brought to the row reduced echelon form by a series of multiplication by elementary matrices. So EA is the row reduced echelon form. If A is invertible, EA is invertible, but EA is in row reduced echelon form, and that is invertible if and only if EA is equal to identity, which means A is which means a square matrix is invertible if and only A is E inverse. Therefore, A is invertible. So using the result that we proved in the last lecture and this observation that a matrix is row reduced echelon form if and only if it is identity, we get that a square matrix is invertible if and only if its row reduced echelon form is equal to the identity matrix. Using these observations, we prove another theorem, that a square matrix is invertible if and only if its rank is equal to its order. Suppose we start with a square matrix of order n and B be the row reduced echelon form of A. Then B is equal to E times A, where E is a product of several elementary row matrices. So E is invertible. Suppose A is invertible, then E and A are invertible, therefore B is invertible. But now B is in row reduced echelon form and B is invertible. So the previous observation says that B has to be equal to identity, which means rank of A is n, because in A we will have A is equal to E inverse, and in E inverse there cannot be any zero rows. Therefore the number of pivots in A is equal to number of pivots in E inverse, which is n. Conversely, suppose rank of A is equal to n. That means B has n pivots. So B is equal to EA. B has n pivots, which will imply that B is equal to identity. In that case, A will be equal to E inverse B, or in other words that is E inverse, and that implies that A is invertible. So A is invertible if and only if its rank is equal to its order. Now what happens if A is not invertible? Let's try to understand the connection between the rows and columns of A. Suppose rank of A is equal to R. Then this means that there are R number of rows, linearly independent rows, and there are R number of linearly independent columns. So mark all these pivotal columns. Now we have shown that in the row reduced echelon form, these pivotal columns are nothing but the pivotal columns are nothing but the standard basis vectors, and the others are linear combination of these pivotal columns. The linearly independent columns correspond to the pivotal columns in RREF of A. So we have R linearly independent columns in A, and other columns are linear combination of these R columns. Also, you look at the first R rows of A. I mean, you look at the R rows of A which are non-zero, which corresponds to the non-zero rows in the row reduced echelon form. So we may assume that they are the first R rows. Now in the elementary row operations, the rest of them become 0, which means that the remaining rows are linear combinations of the other rows, first R rows. So the linearly independent rows correspond to the non-zero rows in the row reduced echelon form. Let's take one example. So we have this matrix A, and this is transferred. This has been transformed to a row reduced echelon matrix in row reduced echelon form. So there are only two non-zero rows. Therefore, the rank of A is equal to 2. Therefore, if you look at the matrix A, the row 1 and row 2 are linearly independent. And similarly, column 1 and column 2 are linearly independent. Now, you can see that column 3 is same as column 5, and it is same as column 1, and column 4 is in fact 3 times column 1 minus column 2. Also in the row, see in the column, this is comes from the row reduced echelon form as well, but in the row 3 is in fact equal to row 1 plus 2 times row 2, and row 4 is equal to row 2 minus 2 times row 1. Now this is another interesting application of the elementary row operations and row reduced echelon form. Suppose you are given m vectors from Fn. So think of it as F1 cross n. You have m vectors. How do we extract linearly independent vectors among these m vectors? The advantage of having linearly independent vectors is that when we look at the span, as we saw in our previous lectures, when we look at the span of these vectors, the linearly dependent vectors do not really contribute to the span, to the information in some sense, which means if u1 up to ur among these are linearly independent and the rest of them are linearly dependent on u1 up to ur, then span of u1 up to ur is equal to span of u1 up to um. Therefore, it is important that we remove unwanted vectors. How do we remove this? How do we get to know which are the unwanted vectors? The elementary row operations and getting to row reduced echelon form gives us one method. Suppose you write this u1, u2 up to um as rows of a matrix A. Then reduce A to its row reduced echelon form. Suppose there are r number of non-zero rows in B. The rows corresponding to these r rows in the RREF of A, that is B, are precisely the number of linearly independent vectors or the rows in A, and the remaining rows are linearly dependent, or they are linear combinations of these rows. Let us do one example. So from these vectors 1 2 2 1 2 1 0 1 2 1 0 minus 1 4 5 4 1 and 5 4 2 1, find the linearly independent vectors. Now let's do the algorithm that we described just now. Write down this vectors as rows of a matrix. Apply elementary row operations and bring it to a row reduced echelon form. So the first set of elementary row operations denoted by O1, we do R2 is changed to R2 minus 2R1, R3 is changed to R3 minus 4R1, and R4 is changed to R4 minus 5R1. So we get the second matrix, and then we do the elementary row operations O2, where R2 is divided by minus 3, R1 is replaced by R1 minus 2R2, and R3 is replaced by R3 plus 3R2, and R4 is replaced by R4 plus 6R2. Then we get to the matrix which is in the row reduced echelon form. So now from here we can make the conclusions. So we have not done any row exchanges, therefore the first two rows, the non-zero rows, corresponds to the first two vectors that we took, that is 1 2 2 1 and 2 1 0 1. So these are the linearly independent vectors. Now the third and fourth are linear combination of these vectors. Now one can easily find out that 4 5 4 1 is 2 times 1 2 2 1 plus 1 times 2 1 0 1. Similarly 5 4 2 1 is 1 2 2 1 plus 2 times 2 1 0 minus 1. So the first two vectors are linearly independent, and the other two vectors are a linear combination of the first two. And as we observed earlier, if you look at the span of these four vectors, it will be equal to span of 1 2 2 1 and 2 1 0 1, and that is also equal to span of 1 2 2 1 and 0, 1, 4 by 3, 1. So this concludes the lecture on rank and linear independence. We will do more properties of matrices and vectors in the later lecture.